Let us consider that a vector field is present in this region, and let us also assume that a surface of area A is kept in this vector field. So it is quite obvious the lines of the field will pass through this surface. Now my dear, if we want to calculate the total number of lines of field that are passing normally through this surface, that are passing perpendicular to this surface at every point, then we require what we call in EMT a surface integration. Its representation as you can see from your screen. My dear, the answer of this surface integration is also called as the flux of the field. The flux of the field through the surface. Now my dear, by now you are very much aware with the method of integration. We have seen each and every detail in the line integrations, isn't it? Basically, what do we do in the integration? It consists of two steps. Overall, it consists of two steps. In step number 1, we find the infinitesimal value of the function, the infinitesimal value of the product by considering the very small differential element. And in step number 2, we integrate all such infinitesimal elements by taking proper limits. As we have seen in line integration, the infinitesimally small element, the very small element, the differential element was the small length dl or dl vector. Similarly, in this case, we are integrating over the surface. So we will take the very small element from that given surface. That means our differential element will be ds. As there was dl, here will be ds. Now, once again, remember in line integration, we have integrated over the path, over the line. In here, surface integration, by analogy, we will integrate over the surface. So let us see what do we mean by the surface integration. First of all, before moving ahead, let me tell you very important point. You know, the area of the surface is represented as a vector quantity and not the scalar quantity in our electromagnetics. For example, let us say I have a rectangle whose length is 10 and whose breadth is, let us say, 5 meter. So of course we will calculate its area by length into breadth, 10 into 5, that is 50 meters square. But in electromagnetics it will be 50 n cap meter square. 50 is of course the magnitude as we calculate by normal formulae as we do in mathematics, length into breadth, 50. And n cap, it is the unit vector, it is the direction. It is the unit vector perpendicular to its own surface. So it is quite interesting. The area of any surface in electromagnetics is represented as a vector quantity. The area vector will have magnitude as we normally calculate in mathematics, and its direction will be perpendicular or normal to its own surface. Now my dear, as you see from the diagram, we can have two possibilities. What did I just say? The area vector will have direction perpendicular to the given surface. Now perpendicular or normal to the given surface will have two possibilities, either this or that. So which one should be taken? My dear, this question is going to become very much significant when we will see the Gauss law in our electrostatics. But as if now, just remember that area of a surface in electromagnetics is a vector quantity. Its magnitude is normally as we calculate in mathematics, and its direction is perpendicular to its own surface. Now let us understand what is the significance of the dot product in the representation of the surface integration. Why dot product? Why not cross product? Let me recall you, when do we need the surface integration? My dear, we need the surface integration when we want to calculate the flux of the vector field that is passing through the given surface. We need the surface integration when we want to calculate the component of the vector field that is passing normally through the surface. So let us consider any vector field is present in this region, and let us assume that in this vector field a surface of area S is present as shown in the diagram. So if I want to calculate the total lines of the field that are passing normally through the surface, or let us say if I want to calculate the component of the field that is normal to the surface, perpendicular to the surface at every point of the surface, then I will be needing the surface integration. So consider any small surface ds, infinitesimally small, having area ds as shown in the diagram. My dear, I have just explained to you any surface, any area in the electromagnetics is represented as a vector quantity. So consider ds vector as shown in the diagram. The area vector has a direction perpendicular to its own surface. And let us assume that the angle between ds vector and field vector is theta as shown in the diagram. Now, my dear, just recall the concepts of mathematics. When do we take the dot product of two vectors? My dear, we take dot product of two vectors when we want the product of magnitudes of one vector and component of the other vector in the direction of this vector. Am I right? So when we take a dot product E dot ds, actually what we get? We get component of the field along the ds vector. And now you know the ds vector, area vector, is already perpendicular to the given surface. So ultimately, we get the component of the field along the normal to the surface, perpendicular to the surface, according to the definition of flux. So my dear, this is the reason why there is a dot product present in the representation of flux of surface integration. It is represented as E dot ds. E is also vector. It is a vector field. ds, small area, differential area. Area is also the vector. So in between two vectors, there can be dot also, or there can be cross product also. But for the surface integration, for the calculating flux of the field, we need a dot product in between E and ds. Once again, I am repeating. When we dot E vector with ds vector, we get component of the E, that means vector field, along the ds vector. And ds vector is already perpendicular to given surface. Therefore, we get the component of the field perpendicular or normal to the given surface.